Okay, we'll review in-class exercise 2 for introductory organic chemistry. Right, so for question 1, you are being asked which of the following is a carbocation as one of the products formed. Okay, so you have to look at the way the arrows are being drawn. So for the case of the first option, you realize that the pi bond is being broken, and then one of the carbon will form a bond with the Br. And take note that this is a full arrow. Okay, it's a full arrowhead. So that means that in the case of this, I would expect the Br to go to this carbon. Okay, and then you have a CH3 here with a positive charge with a Br minus. Okay, because this is a heterolytic cleavage where the sigma bond between the Br, the both electrons, or rather the electron pair in the sigma bond goes to the Br as a bromide. Okay, so there's a new lone pair being formed. So if you wish to do a electron count, you can always write in the lone pair, and then you will realize that going from left to right, you start with 3 pairs of lone pairs. Now for bromides, you have 4 pairs. Okay, then of course you will be thinking, oh, can the Br go to the other carbon? Yes, at this stage, because you haven't learned more advanced organic chemistry, so it is perfectly fine if you write the Br to the other carbons and then you form this particular carbocation. But whatever the case is, you are still producing a carbocation. So therefore, option 1 must be an option that I will pick. Okay, for option 2, you realize that the ammonia here uses its lone pairs of electrons to attack the carbon, and then in this case the CBr undergoes a heterolytic cleavage. Okay, so same thing, I would expect to produce a bromide as well. Okay, so if you do a quick calculation, so there will be a total of 3 lone pairs at the Br at the start, so now you will have 4 lone pairs, and then at the same time I'm going to form a new bond between nitrogen. Okay, so maybe I should draw it. Okay, it doesn't matter. Okay, so I'm going to form a new bond between nitrogen and carbons, and then I'm going to have the H here and the H here. Okay, now because this nitrogen contains 4 bonds, so it will take on a positive charge. Okay, but this is not a carbocation. Okay, so we will not choose option 2. If you look at option 3, this is clearly a homolytic cleavage, so I'm going to produce 2 ethyl radicals, CH3, CH2 dot. So I'm going to get 2 ethyl radicals here. So therefore, I'm not going to choose option 3 as well. So the only option which gives me a carbocation is option 1. Okay, so next I'm going to move on to the second question. It reads, your ethanol can be obtained from the hydration of ethene and then using concentrated phosphoric acid as the catalyst. So basically you're asked to complete the mechanism for the process by drawing all relevant curly arrows. So using the same motivation from question 1, you notice that if the pi bond were to be given an electron pair to the Br, in this case, you will form a carbocation and a new CBr bond. So you can use the same story because I am forming a new CH bond over here. How do I know? Yeah, because originally if you just color code the H's, so I'm having 1, 2, 3, 4 H's. Okay, so the 4 H's remain. Okay, and there's a new H that actually comes from the phosphoric acid over here. Okay, so in the end, I'm going to get a dihydrogen phosphate. So if I'm going to redraw the phosphoric acid molecule, it might look a little bit better. So phosphoric acid actually have a P O double bond, okay, and OH and OH and O dash H. Okay, so I'm just redrawing this whole thing. So this is the red portion which I highlighted. Okay, so I'm going to incorporate the delta plus delta minus here. Okay, so what exactly is happening is that now the pi bond shifts its electron density and attack the H. Okay, and then now the HO sigma bond break towards the oxygen. Okay, so that's how I end up with a H2PO4 minus over here. Okay, so if I'm going to draw this out, it will look like this. P double bond O, and then you have a OH, OH, and a O minus. Okay, I just put in this lone pair of electrons to signify that the lone pairs of electrons actually comes from the original OH sigma bond. Yeah, so I hope this is clear to all of you, okay, listening to this particular review. Okay, so the next thing is you'll notice that this particular H2O, okay, actually the whole molecule goes in. Okay, so again, there is a nucleophilic attack towards the carbocation. So I'm going to draw in the lone pairs of electrons attacking the carbon. Okay, remember you must attack the carbon, you cannot attack the charge. Okay, so because it is forming a bond with the carbon. Okay, so there's a bond being formed between O and the carbon. So the lone pair of electrons must go from the oxygen to the carbon. Okay, and then you form a new bond over here. Okay, why the O takes on a plus charge? You can view it as a formal charge, or you can view it as the whole molecule now has a positive 1 charge, because there must be conservation of charge in the process. Okay, then over here I'm going to redraw this, okay, because I've redrew it over here. Okay, so I'm going to redraw it as P double bond O, O minus, lone pair, and then OH, and then OH. Okay, and then this particular lone pair now will grab one of the H, and then the OH bond will now break towards the oxygen to neutralize the charge. Okay, and in the process, I'm going to produce phosphoric acid back, and that's how it acts as a catalyst. Okay, again, I'm going to color code. Okay, maybe I just put a H here. So I'm going to color code this with pink. So this H is now being transferred over here. Okay, and then the new sigma bond is formed between the lone pairs of electrons on the on the O minus. Okay, and then this is the new sigma bond. Okay, so that's how you should be drawing your arrows, and all the arrows here should be full-headed arrows because it involves the flow of a pair of electrons. Okay, so for the case of the alkene, it involves the flow of the electron pair from the pi bond. Okay, why must it come from the pi bond? Because the pi bond is the weaker of the two bonds, and at the same time the pi bond is at the surface of the molecule, so it is the most accessible to be donated to an electron deficient site. Okay, finally for question 3, you are asked which statement explains why compound X is less reactive than compound Y towards nucleophile. Okay, so in this case you have a ketone. Okay, so if you remember the first video, I was highlighting to all of you that if you have two R groups, we call this a ketone. Okay, and then one R group and one H, we call this an aldehyde. Okay, but for this case, the other R group is also a H. Yeah, so this particular molecule is an aldehyde, but it's a special aldehyde we call it methanol. Okay, yep. So if you look at all the options, option number 1, methyl group are electron donating. You learn about these facts in your introductory organic chem course. Okay, so between page 1 to 27, you learn that the alkyl groups are generally electron donating. So in that case, because the middle carbonyl carbon, it takes on a partial positive charge. Okay, so therefore electron donating here means that the carbonyl carbon here is less electron deficient than the other one in Y. Okay, so this option is absolutely correct. Okay, less electron deficient than the other one in Y. Okay, then for option 2, methyl groups are relatively large compared to hydrogen, so the nucleophile is more sterically hindered as it approaches a central atom. Yes, so remember there are two effects we always need to deal with in organic chemistry or in chemistry in general. Number one is the electronic effect. So electronic effect has got to do with electron donating or withdrawing groups and how they enhances the electron density or diminish the electron density in the reactive site. And then the other effect is what we call the steric effect. So the steric effect is a resultant of the size of the electron cloud, and it will repel or attract. Okay, in this case, most of the time it repels the incoming groups from approaching the reactive sites. Okay, so we can choose option 2 as well. Okay, option 3 is nonsense because it says pi electron in CO is delocalized. So delocalization, remember, it cannot take place between a pi system and a sigma system. Okay, so delocalization, remember I mentioned in the lecture, the criteria is that the p orbital must be parallel. So if this is a pi system and we have another p orbital here, regardless of whether is it empty, positively charged or negatively charged. Empty means it's empty, positive charge means, empty means it's positive charge in this sense. Negative charge means it contains a lone pairs of electrons, okay, or it can also be a radical, okay, it can also be a radical with 1 electrons. So it can also be a radical. So regardless of whether is it like this or like this, okay, or with a positive charge, delocalization can take place. So that means that if we have a system like this with a negative charge, or a system like this with a positive charge, or a system like this with a radical here, okay, we can conclude that delocalization exists between these 3 carbons. Okay, yeah, and that will be the end of my debrief to question 3. Yeah, so if you pick the option question 3, the option to be picked will be B. Okay, so I hope you found the review of in-class exercise 2 educational. So do look out for more such reviews.